In this video, we're going to calculate the pressure, temperature, volume of a gas. So you're going to be able to determine the relationships between temperature and pressure and volume and calculate the changes between them as well. So what we know so far from a lab was that when pressure increases, the volume decreases, which is an inverse relationship. In math, inverse relationships are shown by the letters being right next to each other. So the initial pressure in a volume would be equal to the final pressure in volume. In this case, if the pressure initially was 1 and we doubled it and increased, the volume could be 2 and it halves. So we're seeing pressure is increasing and volume is decreasing, and that actually is true. 1 times 2 is 2, 2 times 1 is 2. They're equal. You can't show them over one another because if I double the pressure and I half the volume because they are opposites, 1/2 is not equal to 2. So this is not how it works. It has to be next to one another. The questions you'll see in class are things like this. What would be the new pressure of a 350 centimeter cubed of gas at standard pressure? Remember, you have a table that tells you about that. Compressed to a volume of 250 centimeters cubed. In this case, the nanoparticles and the temperature are constant. So the pressure was 1 from the reference table, and the temperature initially was 350. And now we're going to a volume of 250 to solve for the pressure. What we're noticing is the volume's decreasing, and what we should know is the pressure should increase, but we need to calculate how much. So we're going to set up a PV inverse relationship where they're next to one another. The first pressure and volume go together, 1 and x, and the second volume and pressure go together, x and 250. When we solve, we divide 350 by 250, so that the 250 cancels on both sides, and our answer is 1.4 atmospheres. Notice that the moles of the gas and the temperature of the gas were not used because they stayed the constant temperature and number of particles. Sorry, I didn't mean to say moles. Number of particles. So that was me doing it. We want to see if you can do the same thing. What would be the new pressure of 100 centimeter cube of gas at 1.5 atmospheres expanding to a volume of 4? You might want to, 400, sorry, you might want to pause the video and see if you can get it right. So the volume was 400 centimeters cubed. The pressure initially was 1.5 atmospheres, expanding to a volume of 400 from the 100, so that was initial volume. You can put them in any order. And the final is unknown pressure. So what we should have known was the volume is increasing, and therefore the pressure should decrease. We just need to calculate how much it decreases by. And yeah, I want you to fill out these tables because it helps us start to think that if I do a calculation the pressure goes up, I know that I did that calculation wrong. So we multiply pressure by volume because they're inverse. And we're going to put the first pressure with the first volume and the second pressure with the second volume. We'll divide by 400 on both sides to get it to cancel, and my answer is 0.3 atmospheres. Again, temperature and the number of particles were not listed, so we're going to keep them same, and we don't have to put them in our calculation. What I'd like you to do is try this on your own now with a puzzle question, and you're just going to put in your right answer. So what would be the new pressure of a 50 centimeter cubed of gas at 4 atmosphere expanding to a volume of 200 centimeters cubed? At this point, you should be able to solve the question, and the way I would have solved it was put in all my pressure and volume values, noticing the volume went up, so the pressure has to go down. Because they're in inverse relationships, so they're always written P times V equals P times V. The first value is going on the left, and the second value is going on the right, and then solving for x by dividing by 200 to get 1.0 atmospheres. We're going to move on to see if you can solve additional questions that are not just P and V. For example, our next case is going to go into P and T. So when pressure and temperature increases, they increase together. Similarly, when temperature increases, the volume also increases, and both of those are direct relationships. So if you're looking at just the pressure and temperature, for example, we're going to put them on top and bottom of one another because if the pressure increases from, like, let's say 1 to 2, and the temperature increases, let's say from 2 to 4, we can see that 1/2 is equal to 2 over 4, and that also works for V over T. It wouldn't work next to one another like P and V were. P and V were next to each other because they were indirect. P and T are on top of one another because they're direct. So an example that I'm going to do says a sample of a gas at 200 milliliters and 25 degrees, what's the volume of the temperature increased to 70 degrees Celsius? Remember that Celsius is a scaled temperature, it is not an absolute temperature, and therefore we can't put Celsius into our calculations, we'll have to change them to kelvins. So let's plug in some stuff in our chart. The volume that we know was 200 to start, and the temperature was 25 degrees, and it changed to 70 degrees, we want to know what the volume is. Since the temperature definitely increases, the volume should also increase, and pressure and number of particles will stay constant. So since it's a direct relationship, we put them on top of one another, and the first volumes go in, the second volume goes in, and then divide by this first temperature and the second temperature. But that won't work because those have to be in Kelvin. So we should be showing it in Kelvin. So I added the 273 here. You can also choose to put it in the chart and just add what it is down here. So you can, instead of it showing it 25 and 273, you can write 298 down here. Instead of 70 plus 273, you can write 343 here, cross multiply and divide, and you can see you get an actually different answer, so it has to be in Kelvin. So now I want to do it together, thinking about this slowly. You have 45 psi, the pressure of this car tire is 45 at 25 degrees Celsius. So again, if you want to just write them in, you can, or you can immediately change it to 298 Kelvin. And then what's the temperature when the temperature changes to 3 degrees? So again, you can write it, or you can just automatically change it to 276. We want to know what the new pressure is. Where V and N are constant, so we're going to cross those out. And we see that the temperature went down, so the pressure should also go down. Oops, down, right? So since they're direct, they do the same thing. We're going to plug them into our PT formula, taking out N and V since they're not important. We're going to write the 45 in the unknown pressure. The temperatures has to be in Kelvin, so I add 273 to both numbers, or you can plug them in the way it would come out in your calculator. Cross multiply and divide, and the answer came out lower than 45 as we predicted at 41.7. Technically with sig figs, I would just write 42. Now you're going to do this. A sample of a gas occupies 150 milliliters at 45 degrees Celsius. What's the new volume when the temperature is decreased to 15 degrees? Okay, so what I would have done if I were you to answer this puzzle question is plug in all my numbers into our chart, noticing that the temperature went down, so the volume should be also going down. It's a direct relationship. We're going to put in our volumes and temperatures. Sorry, that says P, should say V. And plug them in as Kelvin temperatures. So notice that I changed it to adding 273 to both numbers, cross multiplying, and finding an answer of 140 with sig figs, right? So it did go down as we expected, hopefully. At this point, you should be able to determine the relationship between pressure, temperature, and volume and calculate those changes.